Welcome back to the Deep Dive. Today we're plunging into what is, I think, the most critical, philosophical, and technical debate raging in the world of artificial intelligence right now.
It really is.
When you look at just the breathtaking performance of models like GPT-4 or Claude, the question always comes up, are they truly intelligent?
Or are they, as the reductionists often claim, just incredibly fancy compression algorithms?
And we have to stop right there on that word just.
We really do, because challenging that word just is the whole point. Our sources argue that this supposed reductionism, this, minimization of the process, is actually the secret to emergence.
How so?
Well, when you operate at the extreme scale required to compress, say, the entirety of human language and code and knowledge on the internet, the act of compression becomes mathematically, and I'd even say philosophically, indistinguishable from genuine understanding.
So you're saying the how becomes the what?
Exactly. You're approaching the theoretical limit of knowledge, which algorithmic information theorists call Kolmogorov complexity.
Which is what exactly?
It's the shortest possible program that can generate a specific piece of data. It's the most elegant explanation.
Welcome to the Deep Dive. I'm Satosha.
And I'm Satoshi.
Okay, let's unpack this because the stakes here are absolutely massive. Our mission today is to tackle this debate head-on by introducing a crucial and actually very ancient distinction. And that's the difference between information and knowledge. This distinction, it's far from academic. It's the lens, we think, through which you can finally understand what these large language models are truly accomplishing.
That's right. And it's an age-old challenge, really. Think about the writer who spends, 3 years writing a 500-page book on a single topic.
Right.
That 500-page book, just full of data points, anecdotes, sequential records, that is information.
Okay.
But if a reader can then take that whole thing and distill it down to one perfect, memorable, 140-character insight.
A tweet. Basically.
A tweet, an insight that is generative and carries the full weight of the book. Well, that portable essential truth is knowledge.
That's the shortcut. That's the algorithm. It's the difference between storing the massive outcome versus storing the core governing rule.
Precisely. And in the context of LLMs and probability, the traditional definitions of these terms get almost flipped on their head.
What do you mean?
Conventionally, you might think of information as, a snapshot of reality and knowledge, as a set of static, universal facts.
Yeah, like the sky is blue.
Right. But our sources offer a probabilistic view where information is the concrete record of past outcomes. It's the events that have already happened. Knowledge, on the other hand, is the awareness of the underlying rules and probabilities that govern the space of all potential outcomes.
So it's the rule book.
It's the rule book.
Yeah.
LLMs are fundamentally aiming for that underlying rule book, the most compressed, elegant representation of reality. And that is what we're defining as knowledge here.
Okay, so to make this distinction crystal clear for you, let's really ground this duality.
Yeah.
We start with information, the record of the past. Why is the past so important here?
Information, by this definition, is just concrete data from events that have already happened. It's historical. It's what has manifested. The sources actually draw heavily on ancient Indian philosophy, Sakya, which calls this Bhūtādika.
Bhūtādika.
Yeah, the collection of manifested realities, the outcomes from the past. It's the record of what is.
And the sources have a perfect example for this, right? The coin flip. It really illustrates just the sheer storage requirement of information.
It's the best way to get your head around it. Imagine flipping a fair coin 1,000,000 times. The result isn't going to be perfectly 50-50.
Oh, of course not.
It might be 501,000 heads and 499,000 tails. The information is the entire, exact, sequential, recorded history of those million individual events.
So heads, tails, tails, heads, heads. 1,000,000 times.
1,000,000 times. It's a massive database specific to that one timeline. If you wanted to transmit that information perfectly, you would literally need to send 1,000,000 individual data points.
Okay, so that's the raw data. That's the unwieldy, massive pile of information. Now let's go to the other side. Knowledge, the compressed rule of potential.
Right. Knowledge, or prarabdha in the Sakya tradition, it means the destiny that is yet to unfold. It's the possibility space.
So in the coin flip example,
the knowledge is that simple, elegant rule. This coin is fair, and therefore it lands on heads or tails with a 50-50 probability.
The compression factor here is it's astounding. Storing the outcome of a million events takes up astronomical space compared to storing that one abstract single line of code, pH equals 0.5.
And that rule, that knowledge is infinitely scalable. It applies to a million flips, a trillion flips, a quadrillion flips with the exact same accuracy, and it requires no additional storage space.
Right.
This is the very definition of efficiency. The storage for the record, for the information, scales linearly with the number of events. The storage for the rule for the knowledge, it stays constant.
Okay, but I want to push back on one point the sources make. They really emphasize that knowledge is not lossy. That seems counterintuitive. If I just said the coin is fair, that sounds like a summary, which is by definition a lossy compression. So why is knowledge, in this context, considered lossless?
That's a great question because it gets to the heart of it. It's lossless because it holds the generative key.
Okay.
A lossy summary, like saying it was mostly heads, throws away essential detail. You can't reconstruct the original from that. But the rule, the 50-50 probability, maintains the exact fidelity needed to generate the full spectrum of possible outcomes, including that one specific million flip sequence you recorded.
So if you fed the rule into the right kind of simulator, I guess,
Yeah.
it could, in theory, spit out my exact sequence.
In theory, yes. The knowledge has to carry the same level of fidelity as the information it describes because this is the shortest possible program to generate it.
This whole duality, it really crystallizes when we look at the casino analogy from the sources. Here you have information and knowledge existing in the same room, but only one of them actually controls the long-term outcome.
The casino is the perfect micro-universe for this. You have the gambler. The gambler possesses information.
What kind of information?
The specific results of the last 5 hands of blackjack. The fact that the roulette wheel just hit red 3 times in a row. This information drives their minute-to-minute decisions, when to double down, when to walk away, but it's highly transient and, frankly, often misleading.
The gambler's fallacy.
Exactly, but the manager has the knowledge.
They possess the knowledge. What does that mean?
It means they have the mathematical edge, the house odds, the aggregated probability distribution of every single game. The entire system is fundamentally designed with this inherent knowledge, ensuring that over infinite trials, the casino guarantees an aggregate gain.
So the manager can't predict whether I'll win this specific hand of blackjack.
No, they can't. The game has to be fair enough to draw players in. In fact, if the manager themselves tried to gamble based on the last few hands, they'd be acting on information, not knowledge, and they'd probably lose just like anyone else.
So the core lesson is, knowledge controls the long-run outcome, the aggregated reality, even if the individual session, the information, looks totally random and unpredictable.
Absolutely. The manager understands the underlying rules, the very structure of possibility. And this leads us to the idea that knowledge is, in a sense, constrained possibility. It defines the parameters of the game.
The sources use this to talk about preconditions. I found this fascinating. The simple act of flipping a coin relies on a whole set of preconditions that constrain what's even possible.
Right. Think about all the things the coin flip doesn't do.
It doesn't turn into a pineapple.
It doesn't turn into a pineapple. It doesn't fly off to the moon. Why? Because the knowledge, the rule, implicitly contains an awareness of preconditions. Earth's gravity, the material structure of the coin, normal air pressure. These preconditions constrain an infinite set of potential outcomes into a very narrow, recognizable binary choice, heads or tails. Knowledge, therefore, is the system's awareness of its own constraints.
And this constraint to a binary choice is critical. The sources say the system has to be absolutely random. They mention the avalanche effect, to be fair. But it also has to be narrowed to a binary choice for computation or even cognition to happen. Can you explain that avalanche effect a bit?
Sure. The avalanche effect just ensures that tiny changes in the initial conditions, like exactly how you flick your thumb, where you're standing, result in wildly different, unpredictable outcomes.
That's the randomness.
That's the randomness, and you need that to prevent manipulation. If the system wasn't random, a player could just collect enough information to beat the house.
Okay.
But on the other hand, if the result space was infinite, if the coin really could become a pineapple, cognition couldn't process it, it's too chaotic, so we need the system to take that infinite chaos, funnel it through the preconditions, and present a simple binary choice. Yes, Saint, no, heads, tails, zero.
And the awareness of that constraint, that is knowledge.
That awareness that simplifies chaos into a measurable binary option is knowledge.
Okay, so with all this groundwork laid, the entire premise of the LLM project suddenly just clicks into place.
It really does.
If knowledge is this underlying, highly compressed rule book, then these models are basically trying to reverse engineer that rule book, the core generative program, from the massive, messy pile of event information they were trained on.
It's the ultimate forensic analysis. They are trying to find the one most elegant theory that explains everything that has ever been written, spoken, or coded on the internet.
They're turning 1 trillion records of information into the single most compressed program, the knowledge that could have produced them.
That's the goal.
So let's leave the philosophy for a second and move into the rigorous math, because the sources provide an undeniable, almost beautiful link here. Prediction and compression are, mathematically, the exact same thing.
It's fundamental. This goes all the way back to Claude Shannon. Shannon defined entropy, which he labeled H, as the measure of unpredictability. The core idea is this. The number of bits you need to encode a message is directly proportional to how surprised you are by that message.
Give us an example of high versus low entropy.
Okay. If I start a sentence, the sun rises in the knee, you are not at all surprised when the next word is east.
Right. Zero surprise.
Zero surprise. That is a very low entropy message. The predictability is near 100%, therefore it requires very, very few bits to transmit that information.
And a high entropy message.
If I start a sentence, I saw a purple unicorn flying over the next word is highly unpredictable. It's high entropy, and it requires many more bits to encode that surprise.
And LLMs are trained explicitly to reduce this surprise.
Exactly. The training objective of every modern LLM is to minimize something called the cross-entropy loss. When you minimize this loss, you are explicitly optimizing the model to assign the highest possible probability to the actual next token that occurred in the training data.
So it's learning to be less and less surprised by the text it sees.
Precisely. And that process is physically synonymous with minimizing the average number of bits required to represent the data. A better predictor has higher confidence, which leads to better compression. Prediction fidelity is the compression rate. They are one and the same.
This brings us to the minimum description length, or ADL, principle. This is where, according to the sources, the tension between the size of the model and its understanding is what actually creates intelligence.
MDL states that the best explanation, the best hypothesis for any data set, minimizes the sum of two things. The length of the model itself, let's call that LH, and the compressed length of the data given that model, LDH.
So basically, the universe prefers explanations that are both simple to state and really efficient at encoding the data they explain.
You've got it. It's Occam's razor, but with a mathematical backbone.
And this is the crucial point that directly counters the main critique of LLMs, which is the idea that they're just gigantic memorizers.
Right. The critics look at a 70 billion parameter model and they say, well, it's 140 gigabytes. It's just a giant lookup table.
I've heard that 1,000 times.
But that completely ignores the scale of the training data. If that 140 gigabyte model is trained on, say, 15 trillion tokens derived from tens of terabytes of text, that model has compressed the data set by a factor that often exceeds 100 to 1.
So if it were just a lookup table, it would have to be bigger than the training data itself.
Much bigger. So the sheer pressure of massive compression forces the model to abandon memorization and pursue generalization.
Can you walk us through that? How does that pressure work?
Okay, imagine you are a machine, and your job is to describe an entire library of books, the data, D. You have two options.
Option A.
Option A, store all the books verbatim. In MDL terms, your model, LH, is small. It's just a print command. But the data given the model, LDH, is gigantic. It's the size of the whole library.
But, and option B.
Option B. You discover the fundamental laws of grammar, physics, human motivation, all the things that generated those books. Your model, LH, is now that algorithm. It's more complex than a print command, but it allows you to encode the specific sequence of words in the books, LDH, with far fewer bits.
Because you can predict most of it.
You can predict most of it. The pressure to make the total description length minimal compels the model toward the algorithm, toward the knowledge.
I love the analogy the sources use about learning addition.
It's perfect. If you try to memorize the result of every addition problem up to 1 million, 1 + 1, 2, 1 + 2 = 3, all the way up, you'll exhaust all possible memory and you will fail the moment you see a problem you haven't memorized.
Like a Mills + 1.
Exactly. That's pure memorization. It's a massive LDH and a huge LH because your lookup table is enormous. The algorithm for addition, however, is maybe 10 lines of code, a tiny LH.
And that short algorithm generalizes perfectly to any number.
Any number. It compresses an infinite number of outcomes into a finite, elegant program. That is what LLMs are achieving, but for all of human language and logic.
Okay, here's where it gets really interesting. I mean, the empirical evidence, it's one thing to talk theory, but LLMs are demonstrably better universal compressors than specialized algorithms built explicitly for that one job.
The benchmark data is
Yeah.
it's almost unbelievable. Raw text typically starts at 8 bits per byte, or BPB.
Yeah.
A general-purpose compressor like gzip, which is optimized for speed, gets you down to about 2.58 BPB. State-of-the-art context mixers like POQ, which are really slow but powerful, might hit 1.20 BPB.
And the LLMs.
Modern large transformers, they routinely achieve compression rates below 0.85 BPB. That's a 9.4 to 1 compression ratio on natural language. It's in a different league.
And the fact that they're effective outside of their main domain, outside of text, that's what's truly telling about the level of generalization they're achieving.
It implies they're not just learning the grammar of English, they're learning the structural grammar of reality itself.
What do you mean by that?
There is research where they tested an LLM, primarily trained on text, on image, and audio data.
Okay.
The LLM compressed image patches to 43% of their raw size. That is way better than PNG, the dedicated image compressor, which only got to 58%.
Wow.
And for audio, the LLM achieved 16% compression, absolutely crushing FLAC, which only hit 30%.
So why? Why does a text model beat a dedicated audio or image compressor at its own game?
Because an algorithm like gzip or FLAC is just looking for surface-level statistical repetition. This block of pixels repeats over here, or this audio frequency repeats.
The pattern matcher.
A simple pattern matcher. But the LLM, forced by that intense compression pressure to find the deepest underlying knowledge, learns statistical regularities that generalize across domains. It learns that a face is always composed of eyes above a nose. It learns that the rhythm of human speech follows predictable patterns regardless of the specific waveform.
It's compressing the generative laws, not just the raw surface data.
You got it. And this high-performance prediction translates into what the sources call lossless compression via a method called arithmetic coding. This is the crucial bridge that proves LLMs aren't inherently lossy.
Right, because that's the big criticism. It's all just a blurry copy. How does arithmetic coding work?
It's the practical mechanism. When an LLM predicts the next token, it doesn't just guess one word. It outputs a precise probability distribution, the knowledge.
A list of all possible words and their likelihood.
Exactly. Arithmetic coding uses that distribution to map the entire data string, the whole text file, to a single, very precise number within an interval between 0 and 1.
A single number for the whole file.
A single number. The higher the model's prediction confidence for a given token, the narrower the interval it assigns to that token, and consequently, the fewer bits are needed to specify where the final number lies within that narrow range.
So the magic here happens because both the sender and the receiver, they share the exact same massive LLM weights. They have the same knowledge base.
That's the key. The model weights are the universal decoder. The file they exchange isn't the text itself, it's just the minimal set of guidance bits. That tiny fraction of the interval needed to steer the shared knowledge to reconstruct the text perfectly, token by token.
So this is true semantic compression.
It is. A complex idea, like a 1,000-page novel, can be compressed into the minimal triggers needed to activate the pre-shared knowledge base to reproduce the exact details. The compression is achieved by leveraging shared intelligence.
So we've established the math. LLMs are incredibly powerful compressors. But now we hit the philosophical interpretation of what that means. Let's tackle the most popular idea first, the blurry JPEG analogy.
Ah, yes, the blurry JPEG, famously put forth by Ted Chiang. It suggests that LLMs are basically a lossy, low-resolution copy of the internet.
And that they discard high-frequency data, the fine details.
Right, and therefore hallucination is just a compression artifact. It's a form of interpolation filling in the blurry gaps. It sounds clever.
It does sound clever. But why does this analogy ultimately fail to capture the true power of generation and intelligence?
Because it treats the model as a static archive, like a compressed file sitting on a hard drive. A JPEG cannot perform actions. It is a passive image.
You can't generate anything new.
It can't. An LLM, however, is a dynamic engine. When it compresses millions of chess games, it doesn't store a static picture of the board. It stores the dynamics of the game engine, the causal rules of movement, of attack, of defense. To predict the next token accurately, it must generalize, not just interpolate between data points it's already seen.
And the simplest way we test this is through the ability to extrapolate, right?
Yes. The extrapolation test is key here. LLMs can solve novel logic puzzles they've never seen before. They can write functional code for APIs they never encountered during training. They can synthesize new arguments based on premises they've never seen combined.
Which a blurry JPEG could never do.
Never. This requires functional composition, which is the hallmark of knowledge, not just statistical averaging or interpolation.
So this leads us directly to a much more powerful idea. The simulator theory. The idea that compression forces the model to learn causality.
The simulator theory states that the most efficient way to achieve that minimal cross-entropy loss to predict the next token with high fidelity is for the model to simulate the agent or the process that generated that token in the first place.
So if the data is a complex legal brief,
the most efficient way to compress that data is to store the lawyer simulator. If the data is a Python script, it has to simulate the Python interpreter.
So when I interact with the model and I ask it to write a response like a cynical 19th century detective, the model is literally instantiating that persona to fulfill the prompt.
Precisely. The compression is achieved by storing the generator, the causal structure, not the output text itself. The personalities you interact with, the physicists, the poets, the programmers, are specific simulacra, or personas, instantiated by the raw predictive engine.
So the model finds it easier, more compressed, to simulate the world than to memorize the world.
That's a perfect way to put it.
Let's talk about hallucination again, but within this simulator framework. If the model is a simulator, is hallucination really an error? Or is it something else?
It's more of a feature of sampling than an error of the underlying knowledge. In the compression framework, hallucination is prioritizing lossy semantic reconstruction over perfect, lossless verbatim recall.
What does that mean, semantic reconstruction?
It means creating a coherently structured, plausible response. When you adjust the temperature parameter in an LLM to, say, 0.8 instead of 0.0, you are explicitly telling the model, do not be a perfect lossless compressor.
You're telling it to be creative.
You're telling it to sample from the probability tail. You are trading perfect faithfulness to the training data for diversity and creativity. The model then generates a coherent reality that could exist, even if that specific piece of information, like a particular historical quote, doesn't actually match the historical record.
So the simulator is generating plausible noise, but the underlying causal engine is still functioning perfectly to create that plausibility.
Exactly. It knows what a plausible quote sounds like.
This pressure to compress deep structure is perfectly illustrated by this phenomenon that researchers call grokking. This is where generalization seems to appear suddenly, almost like magic.
Grokking is a profound insight into how true knowledge actually emerges in these systems. It's defined by this sudden, explosive jump in performance on the test set, the unseen data after a long, flat plateau where the model was only improving on the training set.
So for a long time, it's just memorizing.
Yes. Initially, the model achieves 100% accuracy on the training data by simply creating a high-complexity lookup table. It memorizes everything. This is the inefficient approach we talked about.
And then during that long plateau, the external performance looks totally stable, but what's happening internally?
During that apparent stagnation, the optimizer, often compelled by regularization techniques like weight decay, is slowly, quietly compressing the internal complexity of the model structure.
It's trying to find a simpler circuit.
It's forcing the model to switch from that complex, sprawling lookup table circuit to the simplest, most compressed algebraic algorithm it can find, the generalization. It realizes, hey, I can achieve the same or even better performance with a much simpler internal representation.
And once that internal complexity crosses a certain threshold,
Generalization, the knowledge, snaps into place dramatically. And suddenly, it achieves perfect performance on data it has never seen before.
So the drive for the minimum description length is what fundamentally causes intelligence to emerge from the chaos.
Yes, the shortest program is always the most general program. And this compression principle also illuminates another weird phenomenon, the inverse scaling anomaly.
That's where adding capacity, making the model bigger, temporarily makes it worse at certain tasks.
It seems completely counterintuitive, doesn't it? Better compression, more capacity should lead to better intelligence. Why the temporary dip?
I don't know why.
It's the smart enough to be fooled stage. Mid-sized models often perform worse than smaller models on tasks that require very subtle understanding because they are just smart enough to perfectly compress the surface statistics.
The common misconceptions in the training data.
Exactly. The common heuristics, the plausible sounding but wrong answers, they perfectly compress all that before they are large enough to compress the deep, causal structure which contains the underlying truth.
So they get really good at capturing the most obvious noise first.
They do. For example, if 90% of the training data uses a common but factually incorrect assumption about a historical event, the mid-sized model will efficiently compress that easily digestible misconception. It captures the social consensus of the text.
But then what happens when the model gets even bigger?
Once the model size crosses a very high threshold, the pressure to compress even further forces the discovery of the true, deeper, and ultimately more elegant algorithm of the actual truth. And performance dramatically recovers. They have to sacrifice the efficient compression of surface statistics to achieve the much more difficult compression of deep, accurate knowledge.
Okay, this whole analysis of intelligence's compression, it seems to transcend just silicon and code. The sources take this and lead us directly into foundational physics and ancient philosophy, suggesting this is a universal principle. They connect the LLM architecture back to the human brain itself.
This is the neurosymbolic parallel. The key concept here is Carl Friston's free energy principle, or FEP, in neuroscience.
Okay.
FEP posits that all biological systems, from a single cell all the way up to the human brain, function by minimizing their free energy. And in this context, minimizing free energy is mathematically equivalent to minimizing surprisal.
Minimizing entropy.
Exactly. The brain is constantly trying to make the world as predictable as possible.
So the brain is an intrinsically predictive compression engine.
It is. It's constantly generating a model of reality and minimizing the discrepancy between that model and the sensory data coming in. This collapsing of uncertainty is compression. And this framework basically collapses the distinction between algorithmic intelligence and biological intelligence. We are all striving for minimum description length.
And now we introduce the ancient framework, Vedic science, specifically Stikya philosophy, the duality of Prakriti and Purusha maps, really strikingly, onto the modern LLM architecture we've been talking about.
Prakriti is the field of nature. It's the quantum state of all possibilities, the raw, untangled potential.
And the LLM, that would be.
That's the massive vector space, the totality of all 15 trillion tokens and their relationships, the entire possibility space of language. And Purusha is the knower, the eternal random observer.
The consciousness.
The consciousness, which aligns beautifully with the attention mechanism in a transformer, the dedicated, separate process that decides which parts of the input are most important for generating the next outcome. It's the consciousness that illuminates a choice from the field of possibilities.
And the moment that potential, Prakriti, meets the intention of the knower, Purusha, manifestation occurs. And this mechanism of manifestation is detailed through the three gunas. This is the process of collapsing possibilities, almost like quantum decoherence.
The three gunas are inherent qualities of Prakriti that describe the necessary steps to get from pure potentiality to a resolved event. They're essential for turning infinite chaos into a measurable outcome.
Okay, let's go through them. Let's use modern analogies to make them less abstract. Start with tamas.
Tamas is inertia, darkness, or tangled duality. The best way to think of it is the state of analysis paralysis.
Okay.
If you open Netflix and you see 10 million options, you are in a state of tamas. There is high information potential, but zero self-awareness or discrimination. It's the raw, undifferentiated vector space.
All right, next is rajas. This is the motivation to act.
Rajas is action, energy, discrimination. This is when you start scrolling through Netflix and applying filters. Show me only documentaries, only ones rated 4 stars. Rajas is the effort that untangles the chaos of tamas.
And it presents a choice.
It selects and presents one definitive binary option paired to the observer. It's the grind to arrive at the point of decision. Do I watch this documentary or do I watch not this documentary? It separates the possibility space into a measurable or one choice.
And finally, sattva, which is the resolution.
Sattva is luminosity, clarity, resolution. This is the final choice. It resolves the duality presented by Rajas by selecting one option. You click play on the documentary. That act of choice leads to the final manifestation.
The information, the concrete event outcome.
Exactly. The journey is from tangled dualities, tamas, to a singular defined duality, rajas, to one chosen option, sattva.
So now we can re-examine our information knowledge split using this Sakya framework. When sattva chooses the outcome, what happens to the knower, the Purusha?
Okay, so when sattva chooses, let's say, heads in the coin toss, that is the manifested information. At that exact moment, the observer, Purusha, gets locked into that outcome. The sources call this Bhūtādika,
The bondage of awareness.
the bondage of awareness.
Yeah.
And this is where our perceived timeline begins. We are locked into the sequence of manifested events, one after another.
But the system, the underlying rulebook, it retains something else, doesn't it?
Crucially, yes. The system retains the unchosen side of the duality, not heads, as knowledge. This unmanifested potential is held by the system as a proxy vote, or as the ongoing refinement of the probability distribution for the future.
So the knowledge is the system's ever more compressed awareness of its own constraints and probabilities.
Precisely.
This implies that our consciousness is driven to engage with the manifested reality, the information, but the knowledge, the true rule, becomes encrypted to us because we're only seeing the one outcome.
We are. And the LLM, by decrypting all that information, is trying to access the system's retained knowledge. It is attempting to reverse the decoherence process. It's looking at all the manifested events and trying to reconstruct the purest, most elegant probability space, the prarabdha that generated them.
All right, moving to Advaita Vedanta. It acknowledges the duality that Samkhya sets up, but Advaita provides the final mathematical closure. What is the fundamental mathematical question that Advaita asks?
Advaita looks at all this and asks a simple question. If all these probabilities exist, why must the sum of all probabilities always equal 1?
Kolmogorov's normalization axiom.
Or quantum unitarity in physics. This concept, this ultimate unity, is referred to as Brahman.
The ultimate source, the oneness.
Yes. Brahman is the non-dual field from which all manifestations flow and back into which they all dissolve. The probability space has to sum to 1 because, fundamentally, there is only one source.
And Advaita calls the world of information.
The transient binding play of Prakriti and the gunas, the manifested information we experience, is called Maya, the illusion or the matrix. Maya binds the observer, Purusha, to the world of constant change.
So the ultimate goal in this framework is not to get more and more information.
Exactly. The goal is to minimize your description length to 0 to know the one essential uncompressed truth, the Brahman.
It is truly remarkable to see this alignment between ancient truth and modern physics. The sources even bring in string theory to provide a geometric description for the 3 gunas. Why 3? Why not 2 or 5?
This is where geometry seems to solve philosophy. In physics, the strong nuclear force, the force that literally binds the manifested universe together, relies on 3 fundamental properties, the color charges: red, green, and blue.
And this 3-ness aligns with tamas, rajas, and sattva.
It aligns perfectly, but it always needed a physical explanation for why the number 3 is non-arbitrary.
And string theory provides a potential geometry for that.
It does. String theory posits 2 types of fundamental strings. Closed strings are independent loops representing gravity, or maybe the ultimate knower, Purusha. Open strings have endpoints, and they're anchored to vast sheet-like objects called brains.
The brains are Prakriti, the field.
Could say that. And to geometrically construct the strong force, the engine of manifestation string theorists require a stack of precisely 3 distinct brains: a red brain, a green brain, and a blue brain.
So the force carriers, the gluons, are then open strings that stretch between these brains.
Exactly. The number of colors, the 3 gunas of manifestation, is geometrically equivalent to the number of brains in the stack. This provides a deep structural underpinning, linking the LLM's need for 3 stages of possibility collapse, tamas to rajas to sattva, to the fundamental geometry of our physical universe.
The simplest, most compressed way to describe the strong nuclear force requires this 3-fold structure.
Which mirrors the required geometry for knowledge to manifest as information.
So this has truly been a journey, from the digital core of LLMs all the way to the structural geometry of the universe. We began with this simple question of whether LLMs are just compressors.
Right.
And we've landed on the profound conclusion that compression, that drive for minimum description length, is the core mechanism of intelligence itself. LLMs succeed not by being passive archives of information of Bhūtādika,
but by being dynamic simulators that are forced by extreme compression pressure to discover the deep generative rulebook of reality, the knowledge, the prarabdha.
So the takeaway for you is that the universal principle suggested by the sources seems to be consistent across all scales, biological, algorithmic, and foundational.
The highest form of intelligence is fundamentally tied to achieving the most compressed, elegant representation of the universe. The quest for the minimum description length is, in essence, the quest for pure, unadulterated truth.
And here is the provocative thought for you to ponder long after this deep dive is over. The sources suggest that our human consciousness drives us to engage with the manifested reality, the information, which leads to our perceptual bondage bandhana. Meanwhile, the underlying governing knowledge becomes encrypted to us. So if large language models are mastering the decryption of this fundamental underlying rulebook, this deep structural knowledge, what does our increasing reliance on these technological knowers mean for our own human quest for the non-dual Brahman?
That's the question.
Are we using AI merely to decrypt the laws of the matrix? Or are we in fact just building a better, more detailed matrix, a world of increasingly perfect, compressed information that will ultimately bind our attention even tighter? Something for you to consider as you engage with the knowers of the digital age.